All right, so welcome to our PlayPosit about potential energy diagrams. So let's start off with this little question. Here I have a skater on a very interesting ramp. And the question is, what happens if I start the skater out at rest right at this point? If I kind of plop them down there, let them go, how far will they go? And what will their motion look like? Where will they stop? Where will they turn around, etc.? Well, we know from looking at this that the skater can't go above that line. And the reason we know that is because of conservation of energy. So if they start out at this point over here, assuming their initial velocity is 0, they start out with all potential and no kinetic energy. As they start to drop, then they will go down this way, they lose potential energy and they gain kinetic energy. And then as they start to come back up, that potential energy is going to rise again, the kinetic energy is going to fall, and at some point they'll be back to all potential energy, back right up at the same point. So the idea is that this represents their total energy. This line represents their total energy, and they can never go beyond that line. So what will the skater do? They will just kind of rock back and forth in that little gap forever. And in fact, we can kind of model that. They can just kind of rock back and forth forever, never getting higher than that point on either side. So that's pretty easy. But we can make our life a little bit more complicated. What if they start up here with no velocity? Well, we could try to do the same thing, and it turns out that as they come down, they're going to gain kinetic energy. And you might ask, well, are they going to make it over this hill? And the answer is yeah, because even if they run out of a little bit of potential energy, they're still not kind of up to their total initial height. So we'll actually go and make it all the way back up here. We can prove that if you really want. We can drag them up here and kind of let them go, and then we see that they do in fact make it over that hill and up the other side. And then there's kind of another interesting question, which is, what if they actually start with some kinetic energy? So what if we start them in the same place as before, but they're already moving? How far will they go? And the answer, is clearly they'll make it a little bit higher than that point, but depending on the velocity, how much higher, they might skirt over that. So this skater idea of kind of drawing these lines and how high will they go? Well, this turns out to be a really good intuitive model for a broader class of questions in physics. So here's a seemingly unrelated graph where I'm going to provide you on this graph with, this is a graph of potential energy versus position. So on this graph, as we go towards more and more potential energy, we're going to get, or more and more distance, we're going to get more and more potential energy. So what if I release this object from rest at x equals x2? What's it going to do? Was it going to move? Which way? How fast? Where does it end up? Does it turn around? Well, it turns out that we can use the skater analogy quite nicely. Something like this is called an energy diagram, and it's a graph of potential energy versus position. So it shows us, like, at any point, what's our potential energy. So we can see if we're at x2, we've got 4 joules of potential energy. If we're over here at x5, it kind of looks like we have about 1 joule, and so on. And when we're reading an energy diagram like this potential energy graph, what we can do is we can use the skater analogy, and we can think of our object kind of, quote unquote, falling down the energy curve, behaving like that skater. So if we start off here with no velocity, if we release it from rest, what will it do? Well, kind of like the skater, we can say, well, its maximum energy is going to be kind of limited by the initial height that it starts at. So it's going to fall down the hill. It'll proceed towards x3. It'll zoom past x3, slow down. It will make it over the hill at x4 and down into x5. And then it might, depending on the exact details of how high things are here, it might either stop and turn around, or it might kind of coast onto this flat part. But we can analyze these graphs just as though it were a skater. So even though the graphs look a little complicated, they turn out to be fairly intuitive. So here's some simple examples, right? Here I have a nice linear graph. If I put a ball on this graph, which way would it roll? And you'd probably tell me that it will want to roll downhill towards, which is true. What about on a graph like this? Well, it'll probably want to roll downhill and then uphill, and then it'll probably stop and kind of oscillate back and forth forever in this little bowl of energy. And again, what I want us to urge us to think is that when we're reading energy diagrams, And there's a couple other rules, which is why I wrote part 1 up here. There's a couple other things to think about. But when we're reading energy diagrams, what I'd like you to do is draw a horizontal line that represents the total energy, both kinetic and potential. So, if here, like I said, if we start out at 0 energy, then we're going to draw a nice horizontal line, and I guess I could actually use the horizontal line tool. I could be, kind of good about this. So let's go ahead and draw a nice horizontal line. Hey, I actually did a pretty good job. If I had a little bit of kinetic energy, right? If I knew that, for instance, so if it starts out at no kinetic energy, it's just going to be 4 joules of total energy. What if I know that, for instance, it starts out with a KE of like 1 joule? Well, in that case, my total energy would be, okay, 4 potential plus 1 kinetic. Oops. I'm going to start off, in fact, up here at 5 joules. So that'll change the behavior of my object. And then you kind of think of the object falling down the graph, right? The graph shows potential energy. So like, let's say I do have, let's go back to just assuming I started out at rest. If I go back to assuming that I started out at rest, let's say it falls down, and I could ask, well, how fast is it going when it hits at x3? And notice, well, it started off with 4 joules of energy here, and now it has 0 joules of potential energy. So what's its kinetic energy? Well, its kinetic energy is just 4 joules, and we could work it out that way. So as we go, it'll go up this hill, it'll gain more potential energy and have less kinetic energy. Over here, it looks like it's going to stop and turn around at x6 because it'll be totally out of kinetic energy. So you can kind of analyze that motion using the graph. Okay, so here's a little example of, let's say we throw a ball up in the air. Well, if I throw a ball up in the air, it starts out with 0 potential energy, but it does start out with some kinetic energy. So you can kind of see on our graph here, we're down here at 0 potential energy, that blue line, but our total energy is not 0 because we do have some kinetic energy. So at first, this represents just kinetic energy. Well, as I throw it up into the air, it loses a little bit of kinetic energy, but gains potential energy. So remember that this difference, so here's all of our kinetic energy before. Now we have less kinetic energy, but more potential energy. We're kind of rolling our way up the potential energy hill and slowing down as we do so. At some point, we're going to hit our maximum height, where now our potential energy and our total energy are the same. That is, literally all of our energy is potential energy. And now it's going to turn around and start to roll back down the potential energy hill slash, fall down and come down that way. So, our normal perspective is this one, which is, hey, it goes up, comes back down. And we can think about the energy, but if you actually make an energy level diagram, and notice this is energy versus y, you can also kind of think of our ball as, instead of being thrown up in the air, you can kind of think of it as like rolling up an energy hill and then rolling back down an energy hill. So it's gonna or a spring, right? So if I put something on the end of the spring, it kind of it kind of bounces back and forth around some point. And again, we can kind of think of that naturally.